Welcome everyone, my name is Vanessa and I will present you today our work, Ultrasound Confidence Map with Neuronal Implicit Representations. Ultrasound is an anisotropic modality, which means same objects in the image look different depending on the point of view. For example, let's observe different scans of the spines. Image in green and image in purple present different values for the same red point. This is caused by the bone in the green image refracting all the sound blocking signals to reach that point, while in purple, observation is correct. One of the popular methods to estimate uncertainty of the accuracy in a given pixels are the confidence map. Due to the physics, more accurate values are closer to the ultrasound probe in the top, but with attenuation, scattering, and signals, the signal gets lost and uncertainty gets bigger. In general, higher certainty values are represented with 1 and less accuracy with 0. Confidence maps have been used before for improving downstream tasks, such as volume compounding from 2D images, shadow segmentation, multimodality registration, and robot ultrasound navigation. Reason why, for us, it's important to improve confidence map. In 2012, Calamares et al. Proposed the calculation of confidence map for any ultrasound image without prior knowledge about its content using a random walk. They formulate the problem as computing the probability of a random walk starting from the top transducer pixels to reach the bottom sync nodes. The random walk is a simple model of sound propagation that takes into account attenuation and reflection on the alpha and beta parameters. However, this method forces all the sync nodes to be 0, which means no sound reaches those points. We propose to calculate the method with just 1 point at 0, the middle one. We will call this adaptation of random walk as the middle confidence map. In 2021, another team proposed the use of an acyclic graph to solve this problem. They solve it row by row, avoiding to fix the confidence to 0 at the bottom, improving confidence maps. We propose now UltraNerve confidence map. It is a physics-inspired neuronal confidence map that, from multiple viewpoints, using overlapping sweeps, learn to characterize the physical properties of the tissue in reflection, attenuation, and scattering maps. UltraNerves produce a new arbitrary render view using those tissues' properties. But we propose to use those maps to create a physics-inspired confidence map, or better call a transmission supervision signal. Our confidence map improves the performance of downstream tasks in which high reflection structures pose a particular challenge, like the bones. Code data and corresponding waves are also available. The method takes the 3D discrete pixels at different t times in a sound array Ri with a specific direction and angle. As output of our method, we generate new render B-mode images, which are compared to the ground truth original images at this position, using a specific loss function that compares similarity between B-mode images and those intermediate maps generated by the method, using some penalization. We propose now, different from UltraNerve, to use these intermediate physics-inspired learning maps to create transmission supervision signal array called an UltraNerve confidence map. Such confidence map can be calculated for the images during the training, but also for new render views at different angles. To test the accuracy of our confidence map, we tried 3 different datasets in 2 different downstream tasks. The first data is a phantom spine dataset with 6 sweeps and more than 2,000 images with CT ground truth label map. This is important. The second dataset is a simulated ultrasound liver dataset with 7 overlapping sweeps and more than 1,000 images, with the bones labels as a ground truth. And the third dataset is our real leg open source available 2D mode dataset of 2D images with tracking. When doing compounding, that is the first downstream task, 3D volumes use 2D images because there are points in the volumes that can only be visualized from specific angles. This problem does not exist in CT because CT is not angle dependent. This is the reason why from CT, we extract the ground truth label map of the vertebrae that is presented here in green on the images. Without confidence map weighting for volume compounding, many surface points are not coherent. They belong to ultrasound artifacts like reverberation and mirroring. But using confidence map, the method provides more weight to the views with higher certainty, decreasing the island and improving the visualization of deeper structures. But using our confidence map weighting, produce a surface closer to the clinical ground truth. From a quantitative evaluation, we calculate the percentage of true positive and false positive points with respect to the CT label map. And we observe that our method has less predicted errors and islands and produce better surface points in deeper areas. Confidence map can also be used to segment shadows with random walks. This is the second downstream task. Our confidence map version do not mark anechoic regions like the veins as uncertainty regions compared to the other confidence map versions, because it observes the same point from different angles to create the sound intensity map. For this reason, the random forests do not select these veins as shadow, which is the case for all the other methods. In terms of qualitative evaluation of a test set, we observe that UltraNerve version performed the best. We can have a long discussion about the time of calculation because remember that our method is patient-specific and anatomy-specific. We will just say that as soon as the method is training on a patient, the inference on a new test set of images takes just minutes compared with the hours that it will take for other methods. The generalization of this method to work in different participants, but anatomy-specific, is a work in progress. To conclude, our confidence map method is based on the physical principles of ecopropagation. It creates new render views and a closer representation of uncertainty map using characterization of tissue physical properties from multiple overlapping sweeps. Our confidence map improves performance in downstream tasks, especially in scenarios where high reflection structures are particularly challenging, like shadow segmentation and volume compounding. Please feel free to use our code and try our method in the 3 available ultrasound datasets. Thank you.